All right, thank you. So today I'm going to start off by giving you some historical context for the connection between math and poetry. And for anybody who didn't know, before I started studying mathematics, I was an English major and was very interested in poetry. And the stuff I'm going to show you today is actually a large part of what made me decide to start studying math, seeing how the poetry that I had been studying could be like relevant to this other scary realm of mathematics. So I hope you think it's interesting as well. Okay, so we're going to talk about a French literature movement called Oulipo, which is short for Pouvoir de Littérature Potentielle. I'm glad French Jerry's not here. Which roughly translates to the workshop for potential literature. This was, it's still active actually. It's an active literary movement that was founded in 1960 by two writers, Raymond Queneau and François Le Lyonnais. Le Lyonnais was actually a chemical engineer and did a lot of writing about mathematics, in addition to writing other kinds of things like poetry. So what is Oulipo all about? Well, so as Liz pointed out earlier, before I started this talk, poetry is all rhymes, right? Or maybe it's all meter. When you think about poetry, you immediately think about like a constraint that you might put on your writing in order to write the poem. And so one of the ideas, the main idea of the Oulipo movement is that the constraint is important and itself kind of a work of art. Okay, so one of the original Oulipian writers said that one of the goals of Oulipo was to demonstrate that literary constraints are, quote, felicitous, generous, and in fact literature itself. And that a goal of Oulipo was to discover new constraints to put on writing to create new literature. Another early Oulipian writer, Claude Berge, wrote in his Potential Analysis of Combinatory Literature that one of the main goals of Oulipo was actually to transpose concepts existing in different branches of mathematics into the realm of literature. So pretty explicitly, one of the goals of Oulipo is to connect mathematics and literature, in particular poetry. So to start out with, we're going to see a couple examples of how that might work. Example number one would be combinatory literature or poetry. And I'm going to start passing around an example of this over here. So I'm passing around something, it's only part of this because I didn't get the cuts right, but this is a work by Queneau, one of the founders of Oulipo, and it is called 100 milliards de poèmes, or 10 to the 14 poems. And so what this is 10 different sonnets whose lines can be interchanged among them. So each poem has 14 lines, and the structure of each of the sonnets is preserved throughout each of the 10 different ones. And so whereas it might be impossible to actually write 10 to the 14 poems, this particular work has the potential to be 10 to the 14 different poems based on sort of a combinatorial rearranging of each of the lines of the sonnet. And so that's only like 5 of the sonnets, I think, but you can still get a concept flipping through, interchanging the lines with one another. That's already like a lot of different poems in there, if you were to look at all the different possible arrangements of each of the lines. And each of them has the same exact structure of the original sonnets. when you rearrange the lines. So we have combinatory poetry as an example. We can write things algorithmically. Okay. So we can write things using algorithms. In particular, a famous example is called the S+7 algorithm. And this is where you take an existing work of literature and every noun gets replaced by the 7th following noun from the dictionary. And this can get weird. I did an example for you. The first stanza of an Emily Dickinson poem. So the original poem is, I died for beauty, but was scarce adjusted in the tomb, when one who died for truth was lain in an adjoining room. And so I ran it through the S+7 algorithm, first using an online dictionary, which was kind of tricky. And that came up with, I died for beaver, but was scarce adjusted in the Tommy gun, when one who died for tsetse fly was lain in an adjoining root beer. I found a dictionary upstairs in the conference room that I tried to see if I got anything better. And that came up with, again, I died for beaver, but was scarce adjusted in the tomcod, when one who died for trypsin was lain in an adjoining roost. So you can see that this idea of just throwing anything into this algorithm is not necessarily going to give you a work of true aesthetic poetic beauty. And it was commented by one of the Olympians, what did he say, that unfortunately it is difficult to invent texts that lend themselves to such manipulations or rules for intervals that permit the conservation of literary quality. So basically we're saying, well, this is an interesting idea, but actually getting something like a quality piece of literature out of it is tricky. And so one of the things that I think isn't clear to me about the poem movement is what is more important, the idea of the constraint that's being formed, or the ability to make something with that constraint. And that feels kind of like a proof of existence versus actually having a definition or a definite formula in mathematics. So we can have this constraint, but we don't necessarily get something beautiful out of it. But the constraint itself is perhaps beautiful. The final example of Olympian poetry, or this isn't a poem even, something called a lipogram. And this is an instance where somebody did manage to write something amazing with quite a hefty constraint. So a lipogram is something written without the use of one particular letter. And the French novelist Georges Perec wrote a novel, a 300-page novel in French called La Disparition, without the use of the letter E. And then people have translated it into English without the use of the letter E. So 300 pages, and there's a plot, and there are characters, and so this is an example of somebody who took that constraint and then actually managed to make it work pretty well and pretty impressively. Yeah, let me see. Anything else? Have we, okay, that's getting around. Okay, so the goal here being to transpose concepts of mathematics into literature. For those of you who are familiar with free groups and presentations, that is my motivation. And for those of you who aren't, I'm going to give a brief overview. Of that. And so what we're going to do is see how to turn this concept from the realm of algebra into a constraint for poetry. All right. Time. When did I start?
5 after.
5 after? Okay. Excellent. Okay, so So this is going to be very quick. If you haven't seen free groups for presentations, it's not super important to understand the poetry stuff that I'm doing, but I do want to show you what the motivation, the mathematical motivation is. So, okay, a group presentation is a set of generators along with a set of relations. And our generators are just going to be, in our case, some finite number of elements, things, doesn't really matter what they are, symbols. And I'm going to take this set along with the set of inverses. And so this is our generating set, is x, oh sorry. And then x along with x inverse gives us what we can refer to as an alphabet, with which we will make words. Sounds like poetry already, right? And so the free group is something where you take any combination of these letters and inverses and then reduce them as much as possible by canceling out pairs of, for example, if you have an x1 and x1 inverse, x2, x3, x3 inverse, then this would be a word on our alphabet, and we will reduce this word by getting rid of the kind of canceling pairs there, and we're left with a freely reduced word. And so all of the freely reduced words on our alphabet make up the free group. We can add more ways to reduce words by adding generators, or sorry, relations. So a relation is a set of generators that reduce down to the identity, typically is how we present them. So an example that we could look at would be two generators with the relation AB, A inverse, B inverse equals the identity. This is going to give us the integer grid. We can think of our generators as being the ordered pairs 1, 0, 0, 1. And this is giving us the commutativity of the integers. And so what we're doing is we're writing words with our generators, and then we're looking to see how we can reduce those words down based on having canceling out pairs, and these relators tell us also how we can reduce words. So for us, our alphabet is unsurprisingly going to be the alphabet. And because I don't want to write with, I don't want to have like A, B, C inverse D, like C inverse isn't really a thing. I'm going to try to give us a lot of relations to work with so that we don't really need to write with inverses. And so let me pass out this thing. Oh, first I should tell you the ultimate goal. The ultimate goal is to write a poem where the body of the poem reduces down to be the title. Okay, so we're gonna write a poem and then look and see how much canceling we can do. And then by the time we cancel out everything that we possibly can, we get down to the title of the poem. Does anybody have questions about this?
I do, quickly.
Yeah.
That is AB inverse, AB inverse? I'm sorry, I haven't looked at this stuff.
The inverse is supposed to be AB, A inverse, B inverse.
Thanks.
Yeah, sorry. Okay. So, pass also right here, let's start some on the other side. So this is a list of pairs of letters, and these are going to each be equal to the identity. And the identity here is the empty word, or nothing at all. And so every time you see those letters next to each other in punctuation, you know that you can cancel them out. So what I want you all to do initially is to just kind of write some words or write a sentence and look at that list of canceling pairs. These are our relations on the alphabet, which is our alphabet. And just kind of mess around with it for a few minutes and see what kinds of reduction you get when you just write something.
I have a question.
Yeah.
If it's a sentence, does like one letter go into the next word? Do you cancel
Oh
the
yeah,
first
great
one?
question. Yeah, so we're ignoring spaces and punctuation and everything like that. And you can wrap around, so if you wanted to write different lines, you can cancel that around from that. All right, has anybody managed to write something particularly brilliant?
You mean that came out brilliant, or the started brilliant?
that came out as something sensible maybe after reducing.
You can sort of make sense of mine.
No. Go ahead.
Well, I started with my Lisa's first sentence that I was just talking about. There is a fly in the house. It came out to E is a fly, E house.
Okay. Thanks. But yeah, so it's not necessarily easy. I hope is what you've taken away. If you just like with the S+7 algorithm, if you just kind of throw something into this system, you're not necessarily going to get something out. So in order to write a poem that fully satisfies this constraint is pretty tricky. Luckily, because the way that I chose these pairs was to take one copy of our alphabet and then match every letter up with a different letter. So basically I have two copies of the alphabet, giving a lot of these canceling pairs of letters. I chose them, I started by looking at a list of the most frequently occurring pairs of letters in the English language to hopefully give more potential to cancel things out. So you'll notice things like Q and U are conveniently paired together. R and E have a double L. And so starting from there and then kind of filling in somewhat haphazardly, the way that I ultimately ended up writing this poem was to start with my title and then add in pairs of letters that I knew would be able to cancel. More or less, that was the process. It was actually a little easier though because I gave myself maybe even a little more structure than I originally intended. So you'll notice that I have A and S. This equals the identity, which means that A is equal to S inverse. But I also have down the list S and T are equal to the identity. And so T is also equal to S inverse, which means that A and T are the same within this system. And if you go through this list of pairs and examine all of the possible equivalences, then you actually get a lot of them are the same as one another. And we have these 12 classes of letters, and so a bunch of them are the same. These are all the same. These, and then the rest of the letters stand sort of on their own. And so because of all this extra structure, it made it a lot easier if I said, okay, well, I'm just going to pick whichever representative I want out of these classes of letters and use that to write my poem and use that to cancel. So in fact, a lot of these will cancel out with each other, far more than just that original list informs you. So here is the actual poem that I managed to write using this system. Does anybody want to give a dramatic reading?
Come
No?
on.
No?
Well, it was just Halloween. Come on, something must be.
Yeah, this This is
All
thematic.
diplomatic reading.
Thank you.
Grave. Fog in the rising wind. Wringing hand of a boy. A quivering hint. The chilling air. The erasing of all there.
So yeah, I'd like to revisit the part where it says, where Claude Bear says something about conservation of literary quality. I personally think this is a pretty cheesy poem, but it is more of a proof of concept that it's possible, you'll see, to write a poem using this particular constraint, even though it might not necessarily be the best. So, problems with this, I feel like I'm cheating by interchanging my use of the letters that are equivalent to one another. So it seems like a more robust constraint would be to not allow for this, to kind of give it a little less structure, or rather, to not allow myself to change around representatives of the equivalence classes. Does that make sense? So have fewer of these is really what I mean. So have more standalone letters when I go through the canceling pairs, because that did make it significantly easier to write.